All right, so yesterday we were doing some curve sketching using the algorithm. We'll try to do the same thing today. It's a little bit tricky for sure, and there's always a long question on the exam or test asking you to sketch something precisely. So it's a very common question, and you need to know how to do it. So we're gonna do some more of this. I'm gonna write down on the one side of this page what the algorithm actually is. So first you want to find the x and the y-intercepts. Then you want to find your asymptotes in whatever form they may be in. So vertical asymptote is only for rational functions, doesn't apply to polynomial functions. Horizontal asymptote, there's three cases. Depends on whether the degree in the numerator is bigger, smaller, or equal to the degree in the denominator. And if the degree in the numerator is bigger, then you have an oblique asymptote. So these you can swap them around. You can do asymptotes first and then x, y-intercept second. This order doesn't matter. And then the third one is you find your critical values. Do you remember how to find the critical values? That's when you set the first derivative equal to 0. And these will give you your turning points. Turning points. And using the critical value, we can make a sign chart. That's what we did yesterday. And sign chart will give you whether your function is increasing, decreasing. It'll give you your local mins and local maxes. Could also potentially be absolute mins or maxes if it's a even degree polynomial. Something like this. That would be an absolute max, whereas this one would be a local max. This one doesn't have an absolute min, but it does have a local min right here. So that's what the critical value gives you. And then the last piece is the point of inflection. Do you remember how to get the point of inflection? You want to set the second derivative equal to 0 and solve for x. So that gives you the point of inflection, which is essentially the concavity of your graph. Again, you want to make a sign chart. So this one, if it's positive, then that means you're concave up. If you're negative, that means you're concave down. So there you go. That's the algorithm. And hopefully with this information, you can sketch the curve as precisely as possible by hand. All right, let's start. This one's not that difficult. It's just a linear over a quadratic. I'm just gonna factor this just to see if I can cancel out the x's. What does x squared minus 25 factor to?
Just x minus 5.
So it'll be x minus 5, x plus 5. It's a difference of squares. So nothing really happened here, which is fine. All right, so let's start with the top one, the x-intercept. How do we find the x-intercept of this?
You set the y to 0.
All right, y is 0. Now what? How do we solve this for x? It's easier than you think.
By the denominator.
Yeah, denominator is gone. Multiply both sides for the denominator, it disappears. And then divide both sides by 2. That gives you an x is equal to 0. If your x-intercept is 0, y-intercept is automatically 0. Don't even have to check. Okay? So that's number 1 done. Next, let's work on the asymptotes. Does this have vertical asymptotes? So vertical asymptotes is for rational functions, such as this one. Something with a denominator. So to find the vertical asymptote, you first factor it, okay? You have to first factor it and see if anything cancels out. Nothing cancels out here. And then what we do is that we set the denominator equal to 0. So you can either set this or the factored form. I'm just going to set the factored form equal to 0. All right, so where are my two x-intercepts?
5 and -5.
Yep, plus and minus 5. Horizontal asymptote. Again, you need to compare the degree of the numerator with the degree of the denominator. If the degree in the numerator is less than the degree in the denominator, then your horizontal asymptote is at y equals 0 on the x-axis, okay? Here's a note about these asymptotes. Vertical asymptotes, your curve will never cross, will never pass it. This is a hard wall. I'm gonna call this, I don't know, like just think of a wall made out of concrete or something. It's a hard limit. It's a hard barrier. Whereas a horizontal asymptote, you can pass it. So it's like a wooden wall or something, like a plywood wall, very easy to pass. And you usually this will pass, and then I'll just write this down as well. Usually it'll pass at the intercepts. Usually passes at x-intercepts. Like that. So that's done. So let's just sketch it really quickly, a rough sketch of what we have thus far. So we have x-intercept, y-intercept, and our asymptotes. So x-intercept is 0, y-intercept is 0 right there. That is fixed. Our asymptote is plus minus 5. So 1, 2, 3, 4, 5 here. Negative 1, 2, 3, 4, 5 right here. So negative 5 is there. That's an asymptote. Positive 5 is here. And we also have an asymptote on the whole x-axis, the horizontal asymptote, y equals 0. So that's what we have right now, which doesn't really help us that much, to be honest, which is fine. Next, let's find the critical values. Remember what critical values are. They are turning points. To find the critical values, what do we do?
We set the first derivative to 0.
Right, so let's find y prime. So we're gonna find y prime, set it to 0. So what is y prime here? You have to use quotient rule. And that's your quotient rule. What's the derivative of 2x?
2.
2, so you multiply, that's f prime. You multiply g as it is, so g is your denominator there. So this is f prime g, I'm following this formula, minus f as it is, so f as it is 2x, times, what's g prime?
2x.
It's 2x, all over g squared, so x squared minus 25 whole squared. So there you go, this is our equation that we need to solve. We're setting this equal to 0. Does the denominator disappear? If you multiply both sides by the denominator, does it disappear? The answer is yes, it does, right? The denominator is gone because you're essentially multiplying it by 0. So you get negative 2x squared minus 50 is 0. Which will be negative 2x squared is positive 50. X squared is negative 25. If x squared is negative 25, what's x?
It's 5.
So we're looking for a number. When you square it, you get negative 25. Does it exist?
No.
No, it does not. Negative 25 has no squares. Positive 25 does, but there's no number. When you square it, you would get negative number. Whenever you square something, you will always get a positive number, okay? So what does that mean for us? It means that there are no turning points on this curve. Cool?
Mhm.
So we'll never see like a U-turn on this curve, which is fine as well. Like for example, 1 over x looks like this. This one doesn't have any turning points. These are not turning points. Turning points is the vertex. If you were to follow this line, it's going to go to infinity forever. There are no turning points here. So let's forget about the turning points. Let's work on the second derivative. Let's see if this one has a point of inflection. So when you factor the first derivative, this is as far as you can go. 2x squared minus 50 minus 4x squared is negative 2. Yeah. So this is as far as you can go. This is your y prime. Now we need to find y double prime, and we need to set that equal to 0 to find the point of inflection. What's the derivative of this? You have to use the quotient rule again.
Negative 4x.
So negative 4x.
50.
No, not minus 50. The derivative of minus 50 is a 0, so it's gone. Times the denominator minus f as it is times the derivative of the denominator. What's the derivative of x squared minus 25?
2x.
2x. And all over, there was supposed to be a squared here. Yeah. All over that denominator squared. Now remember, a squared squared is a4. The exponents, they multiply. So we already have a squared term here. When we further square this, this becomes x squared minus 25 to the power of 4, like that. And we're going to set this equal to 0. So this is for y double prime. Does the denominator go away? What happens if we multiply both sides by the denominator? Does it disappear?
Yeah.
Yeah, it's gone. So we have 0 is equal to negative 4x cubed plus 100x, gonna be very careful here, minus negative 4x squared minus 100x. And when you open this, this becomes a plus 4x plus 100x. Plus. So this is negative 4x squared plus 4x cubed plus 4x squared plus 200x equals 0, like that. Can we factor out anything?
A 4x.
A 4x. So we pull out a 4x, we're left with negative x plus, so we're left with negative x squared plus x plus 50. Does it seem right?
Mm-hmm.
So what does this mean for us? Where is our point of inflection? If 4x is equal to 0, what's x? It's 0, okay? It's a 0 from this. And again, we have to set this equal to 0. I'm trying to think if we can man that. I don't think we can man this. Multiplies to negative 50, adds to 1. 10, 5 doesn't work. 25, 2 doesn't work. Yeah, I can't really think of anything that would add up to 1. So you need to use the quadratic formula for that, okay? So this also gives me, from the quadratic formula, I would get negative 6.6 and 7.6 for this. Now let's go back up to our sketch. So we know that this one has no turning points, but we have a point of inflection right here at 0. Now what we're gonna do is that we're gonna make a sign chart. And I'm not super concerned with these -6 and 7 because they're further away from my asymptotes. I'm primarily concerned with this 0 here. So what I'm going to do is I'm going to make a sign chart. Whenever you make a sign chart, you need to incorporate your vertical asymptotes as well. So our vertical asymptote was ±5. So -5 is here, +5 is here, and our point of inflection is a 0 right here. So these are the 4 boundaries that I'm going to check using my sign chart. So I would go from -∞ to -5, -5 to 0, 0 to +5, 5 to +∞. And this was a point of inflection, so we would be checking this on F double prime. So this guy. When you factor that guy, the denominator stays, and then in the numerator, that factors out to this thing that we have here. So essentially what y double prime is it is 4x times -x² plus x plus 50 all over x² minus 25 to the power of 4. So this is our f double prime. I'm going to check for this. So we're going to split this up to make our life easier. So I'm going to do one at 4x. I'm going to do one at -x² plus x plus 50, which looks like this. It is negative to the left of 6.6, and it's negative to the right of 6.6. This is the graph of -x² plus x plus 50. Those x-intercepts I didn't show you, but we got it using the quadratic formula because it was not manable. So those are the two components, and the bottom component is x² minus 25 to the power of 4. And this entire thing, when you multiply them, that is our f double prime. Let's focus on this one because this one's easy. Doesn't matter what number you put in as x, you're taking it to the 4th power. So now think about it. If you take something to the 4th power, does it become positive or negative? Positive. So it doesn't matter what number you put in here as x from any of these boundaries, your number, final answer, will always be positive because you're going to take the 4th power. So this is plus, this is plus, this is plus, this is plus. For this guy, it's a little bit tricky. Okay, so from -∞ to -5, I'm just looking at the value of -6. Looks like it's going to be negative. From -5 to 0, looks like it's going to be positive. From 0 to 5, looks like it's going to be positive. And then from 5 to infinity, I'm looking at the last section here. It looks like it's going to be negative. For 4x, if you plug x as a large negative number, what do you get?
A negative number.
A negative number. Here, if you plug -1, you get a negative number. Here, you get a positive number. Here, you get a positive number. Now you multiply the signs. This will give you a positive. This will give you a negative. This will give you a positive. This will give you a negative. Is that right? Yeah. Is this making sense? What this ultimately means is that from -∞ to -5, our curve is concave up. From -5 to 0, our curve is concave down. From 0 to 5, our curve is concave up. And from 5 to infinity, our curve is concave down, okay? So we have up, down, up, down. So that's our thing. Here we're up, here we're down, here we're up, down, down. Are we good so far? Hopefully we are. Now look at this. There's only one way this is gonna work. It has to be concave up here, right? Even without putting in any points, is it gonna be this top one or is it gonna be the bottom one? What do you think? Which one is concave up? Concave up is something like this, right? Like that. Because we need a concave up here, it's gonna be the first case, yeah? Like that. Same thing here. We need this to be concave down. Is this concave down or is this concave down? Up or down?
Down.
Down, exactly. So we know we're coming here from here, and then we have to pass through 0, and that is our point of inflection. At a point of inflection, your concavity changes. So as you can see here, down, up, boom, like that. And then finally, on the last section, it's concave down. There's no way it's going to be up top because that's concave up. So it must be down here, even without checking any points. And there you go. Final answer for this question. Did that make sense? So there you go. That's how you sketch a curve. Using ideas from first derivative, from the second derivative, okay? Let's do another one, because this is the entire chapter, basically. Then this is the end of the line for this topic. Let's do one more. Which one seems really nice? Let me think. Let's do this one, because why not? All right, we'll start up here. How do we find the x-intercept?
You set y to 0.
All right, y is 0. Let's do x squared minus 3x plus 6. The denominator disappears. Remember that, because you only multiply both sides by x minus 1. Can we man that? We're looking for two numbers that multiplies to 6, but adds to -3. Is that possible? What do you think? The only two things multiply to 6, right? 2 and 3 and 1 and 6. There's only two combinations. And no matter how you add them, it'll never add up to 3. Doesn't matter what's positive, what's negative. So you can't man this, okay? Now the question is, does this even have x-intercepts? Let's use the quadratic formula. A is 1, B is -3, C is 6. Quadratic formula says the x-intercept is at -b plus minus b squared minus 4ac over 2a. -b is 3, plus minus b squared is 9. 9 minus 4 times 1 times 6 over 2. Now I want your attention just here on this one section. We have 9 minus 24. 6 times 4 is 24. So in this square root, we have 9 minus 24, which is the square root of -15. Can we take the square root of -15? Or any negative number? Can we square root a negative number? We cannot square root negative numbers, okay? If you remember, the square root function looks like this. It starts at 0, 0. It cannot take any values less negative. The minimum value is 0. You cannot take the square root of a negative number. Why can't you take a square root of a negative number? Because let's say the square root of a negative number is some value x. From the definition of square roots, when you square both sides, well, the square root cancels out with the squared, you'll get x squared equals -15. But we know, doesn't matter what number we have, positive, negative, if we square it, we will always get a positive number. There's no way to get a negative number when we square something. That is why the square root of 15 is impossible on the real number system. If we're talking complex number, it's doable, but we're not talking about that here. -15 does not have, you cannot take square roots of a negative number, which means you cannot solve this. This one is unsolvable. What that means for us is that it has no x-intercepts. Anytime you get a negative number inside your square root, if you're trying to use the quadratic formula, it has no x-intercepts. we say it has no real roots. That's the terminology, no real roots. So x-intercepts does not exist. What about y-intercept? Where's the y-intercept for this guy? How do we find the y-intercept?
You set the x's to 0.
Yep. So you find f of 0. So look at this. If you find f of 0, this becomes a 0. This becomes a 0. 3 times 0 is a 0. This becomes a 0. So what you're left with is 6 over -1, which is -6. So your x-intercept is -6. Next, let's talk about vertical asymptotes. Vertical asymptotes only exist for rational functions, and you need to set the denominator equal to 0. For vertical asymptotes, first factor it, and then you set the denominator equal to 0. This one is unfactorable because we couldn't man the numerator. So where do we have the vertical asymptote here? If you set the denominator equal to 0, what do you get?
0.
No. You'll get 1. So look at this. X minus 1, right? It's not that difficult. Look at this. X minus 1 equals 0. X is 1. So that's your vertical asymptote. Horizontal asymptote does not exist for this function. Why? It has something to do with the degrees. There is no horizontal asymptote here.
The degree of the numerator is bigger.
Yeah. So when that happens, we get an oblique asymptote. For oblique asymptotes, you have to do long division. I'll show you both ways actually, because I don't know if you're comfortable with this. I'll show you both ways. You can do long division. You can do synthetic division. I prefer synthetic division if your divisor is linear because it's much quicker, but I will show you both ways. The long division method, this is your divisor. Everything in the denominator, whatever you're dividing by, always comes out. The numerator is called the dividend, whatever you're trying to divide. So x squared minus 3x plus 6. On the synthetic division, you need to set the denominator equal to 1. Sorry, equal to 0, which will give you 1, which is also your vertical asymptote. And then inside, you only have the coefficients. So 1x squared is 1, -3x is -3, 6 is 6. In synthetic division, this first number always comes here as it is. And then you multiply it with the divisor. So for the next term, it'll be 1 times 1, positive 1, and then you add them. -3 plus 2 is -2. -1 times -2 is -2. You add them 4. So because we had an x squared in the numerator, we divided this by x. The power of this is x. So that's what we're looking for. We're looking for the quotient. So the quotient is going to be 1x or x minus 2. And that's your vertical asymptote. It's not vertical, oblique asymptote. This is your remainder. We don't care about the remainders in oblique asymptote situations. So that's how you do it using the synthetic division, using the long division method. And sometimes you have to do this if your divisor is more than degree 1. You want to ask yourself, what do I multiply by x to get x squared? What do we multiply x by to get x squared? X, and then you do x times x, x squared, x times -1, -1x. Here, instead of adding like we did in the synthetic, we subtract. X squared minus x squared gone. -3x plus x is -2x. Once you cancel out something, you're allowed to bring the next guy down. What do we multiply x by to get -2x?
-2.
-2. So -2 times x, -2x. -2 times -1 is +2. And then we subtract them. -2x minus 2 plus 2x is 0. 6 minus 2, 4. This is your remainder. This is your quotient. So you can do whichever way you want. I prefer synthetic. It's quicker. but you need to know how to do long division in case your divisor is x squared or x cubed or something. So that is the quotient is the oblique asymptote. So our oblique asymptote is at x minus 2. All right, next we're gonna find, oh my God, this is gonna be annoying. We need to find the first derivative set equal to 0. Let's see how difficult this is. Shouldn't be too bad. Let's try it. So the first derivative here, I'll do it. It's gonna be 2x minus 3 times 1 minus x squared minus 3x plus 6. What's the derivative of the denominator? It's a 1.
1.
Yep. All over g squared, so x minus 1 squared. We said that equal to 0. So this gives negative x squared. Let me just write it in this one. The denominator disappears, but you will get 2x minus 3 minus negative x squared plus 3x minus 6 is equal to 0. This gives negative x squared plus x minus 9 equal to 0. Is that right? Seems right. All right, just for the sake of time, again, I think you have to use a quadratic formula here because the only things that multiply to 9 is 3 and 3 and 1 and 9, and there's no combination that would ever add up to a 1. So I'm setting this equal to 0. Turns out when you do use the quadratic formula, you'll again get a negative inside the square root. What does that mean for us? We're trying to find the critical values. We got a negative inside a square root. So do we have any critical values? Yes or no?
No.
No. Why? Because we got a negative in the square root, right? Is that right though? Let me just see. A 2x minus 3 minus times 1 minus negative x squared plus 3x plus 2. Okay, I messed it up. This should have been 5x here. 5x. Does that change anything? Multiplies to negative 9, adds to 5. 3 and 3 doesn't work. 1 and 9 doesn't work. Okay, that doesn't actually change much because it still doesn't have any x-intercepts. So we didn't find any critical values. Cool? Next, let's find the second derivative. So this is our first derivative. When you clean this up, you get negative x squared plus 5x minus 9 all over x minus 1 squared. So this is our y prime. What'll be our y double prime? So it'll be negative 2x plus 5 times x minus 1 squared minus negative x squared plus 5x minus 9 times 2x minus 1. Okay, this is getting complicated. And this becomes x minus 1 to the power of 4. And then this should give you points of inflection if there is, but I really don't want to solve this because it's not easy. Yeah, you'd have to first open this bracket, and then you would get a cubic function, which is going to take its sweet time. Right, so what do we do? What's the best way to graph this? Let's see what a rough sketch looks like. Y-intercept of negative 6. X-intercepts don't exist. And then we have a oblique asymptote of x minus 2. So our y-intercept is negative 2, and then you go 1 unit up and go 1 unit across, something like that. So our oblique asymptote is right here. Let me just double check something, because in a graph like this, there's only two possibilities usually. Either you get something like this, which doesn't make sense for us. Why? Because if it looked like that, yeah? Look at this. there should have been an x-intercept if it looked like that. But we don't have an x-intercept, so it definitely doesn't look like that. The other possibility, again, let me just show you the two possibilities. I'm gonna change the color here. I know it looks weird, but this was the first possibility. I just want to make this clear. And that first possibility fails because we should have gotten 2 x-intercepts. If that was the case, we don't have any. Now, the only other way to write that asymptote is like this. Yeah? That's the only other way. But if it did look like that, we should have had critical values because there's a vertex here. So the fact that we don't have x-intercepts means I'm pretty sure it looks something like this, which means our first derivative math is wrong because there should have been a vertex. So let's just redo the first derivative math just to double check. So again, we're trying to find the first derivative. 2x minus 3 times x minus 1. Again, this is f prime g minus f g prime. Minus f is x squared minus 3x plus 6. G prime is a 1. And then we have x minus 1 squared. I don't know if this looks different than last time, but we should have 2 vertices here. So this is 0, denominator is gone, see you later. Let's open this bracket. 2x squared minus 2x minus 3x plus 3 minus x squared plus 3x minus 6. X squared minus 2x minus 3 is equal to 0. X minus 3, x plus 1. Okay, there we go. I don't know what went wrong. Something went wrong last time. But we do have 2 critical points. One of them is at positive 3. One of them is at negative 1. Cool? And our vertical asymptote was at 1, right? Okay. So again, now we can kill this. So this is our vertical asymptote. It's at a 1, right? Our critical value is x equals 3. Now we know it's not here. We just decide for that it's not there because we don't have an x-intercept here. So you see this point up here? What's the x value? What do you think the x value there is? It's the vertex up there. 3. This 3 represents that turning point for the upper curve there. That must be 3, okay? To find the y value, you'll just plug it back in here. But we know that that x value is 3. Similarly, at x equals negative 1, so I have to modify this graph a little bit because right now it looks like the vertex is there, but the vertex is actually at negative 1. So our graph should look something like this. So it's going to peak at negative 1 and then it's going to go down. This peak right here is going to be at negative 1. Let's double check this. So we have Desmos start graphing. So x squared minus 3x plus 6 divided by x minus 1. There we go. So that's our vertex, 3, 3. I didn't plug the y value in, but the x value there is 3. Same thing down here. The x value here is negative 1. And the y-intercept we found it was negative 6 and doesn't look like there's any x-intercepts, just like we predicted. Did this make sense? So that's how you sketch a curve. And sometimes just by practice, right? Like I know there should have been a vertex here because the other sketch didn't make sense, which meant I was able to correct my mistake. Let's keep going, I guess, because this is pretty fun. Let's try this one. Let's find the x-intercept. Remember, x-intercept, you set the y equal to 0. So 0 equals 1 over x squared minus 4x. How do we solve this for x?
You multiply.
You multiply by the denominator, so the denominator disappears, so you get 0 equals 1. What does that mean? So if you see weird math, right, it just means it doesn't exist. That's it. Can 1 be equal to 0? No, right? No, it cannot be. So if you ever get a weird math like this, it just means that, well, the x-intercepts don't exist. So x-intercept does not exist. What about the y-intercept? How do we find the y-intercept?
You set the x's to 0.
Right? So we get 1 over 0 squared minus 0. What is that?
It's nothing.
It is nothing, right? So does it have an x or a y-intercept? No.
It doesn't.
No x-intercept, no y-intercept. What about the horizontal asymptote? Degree in the numerator is less than the degree in the denominator. What does that mean for horizontal asymptote?
It's 0.
It's 0. Vertical asymptote, you have to just set the denominator equal to 0. So x squared minus 4x is equal to 0. How do we solve this for x?
Divided by -1.
So x squared minus 4x is equal to 0. Remember, to solve any quadratic, any polynomials, you always factor it. So what you should do here is you should take out an x. You're left with x minus 4 equal to 0. This means that either x is 0 or x minus 4 is equal to 0. These are your two asymptotes at 0 and at 4. So at x equals 0 and at x equals 4. So let's do a rough sketch. So we have something like this. Horizontal asymptote. So we have an asymptote on the x-axis, but now we also have an asymptote on the y-axis, which makes sense why we don't have a y-intercept. And there's one more at 4. So 1, 2, 3, 4. So this is what we have. Notice we have two vertical asymptotes. That means our curve is going to have 3 sections, basically. We're going to have something here between these two. We're going to have something here. We're going to have something here. There's always n plus 1 segments to the curve, where n is the number of vertical asymptotes. So 2 vertical asymptotes, your curve is going to have 3 different sections. Cool? All right, now what? Let's find the first derivative. Let's see if we can find the critical values. So critical values are turning points. To find the critical value, you set the first derivative equal to 0. What is the derivative of this?
It's 1.
So again, remember, this is f, this is g, right? Quotient rule says f prime g minus f g prime over g squared. What's the derivative of 1?
Is it just 1?
Is 0. The derivative of anything is a 0. So f prime is 0. 0 times g as it is, this entire thing is a 0. So you can ignore that. So I'm going to start from here. Minus f1 times g prime. What's the derivative of g?
2x minus 4.
2x minus 4 all over g squared. So x squared minus 4x squared. When you open this bracket, you'll get negative 2x plus 4. How do we solve this for x? You multiply the denominators, disappears. So x will be 2. Negative 4 over negative 2x is 2. So there you go. We have our critical value. So we have a turning point at 2. So 1, 2, we have a turning point somewhere. So it's either going to be up or down. To check if you're up or down, you plug this into the function. Now let's find f of 2. That's 1 over 2 squared minus 4 times 2. We're just interested in whether this is a positive or negative number. It's a negative number. Yeah?
Mhm.
So are we above the x-axis or below the x-axis? Below. So we know now there's a turning point at 2 and negative 1 over 4, 2 1/4. So let's say right here, there's a turning point right here. What does this mean for us? Well, the only way this is going to work, remember, we have no x-intercepts, and you want to make sure where the asymptotes are. There is no way that that function is coming from up there and going like this. Because if it was like this, then we would have two different x-intercepts. The fact that we don't have x-intercepts means there's only one way this is going to work, is if our function comes from down here, goes through that vertex, that turning point, and then goes right back down. There we go. We have that section in the bag. Now what? We need to find, so it's either going to be here or here, and it's either going to be here or here. We could plug points in, but sometimes they don't get you full points for just plugging and chugging, because anyone can do that. So I think we can decipher whether it's up or down by finding the concavity, by finding the second derivative, and we can see whether it's concave up or concave down. So let's try that approach. You could always plug points in, by the way. If you just plug, so this is 4, this is 0. If you plug f of -1, if it gives you a positive number, then it looks like this. If it gives you a negative number, then it looks like this. That's the easy way of doing it. But like I said, sometimes they don't give you the points for not doing it using the concavity method in this course. So to do that, we have to find the second derivative. So this is your first derivative. Let's find your second derivative. So that's going to be -2 times x squared minus 4x squared minus -2x plus 4 times the derivative of this. Again, this is going to be tedious. Times 2 x squared minus 4x times 2x minus 4 all over x squared minus 4x to the power of 4. So that is the derivative. If you open this bracket, you're going to get x power 4, which is really annoying. Let me see, actually, I'm going to try and do this by hand. So we're setting this equal to 0. The denominator disappears. So 0 is equal to, let's see if we can hand do this, -2. Don't open this bracket. If you open this bracket, you're screwed. This minus so here, this is minus 2x plus 4. If I take a minus sign out, I would get 2x minus 4. So I'm going to write it like that. So minus 2x plus 4, I'm going to write this as minus 2x minus 4. Negative negative becomes a positive. And now we have 2x minus 4 squared, because this and this, there's a 2 in the front. And then there's also this, x squared minus 4x. Like that. Now what I'm going to do is I'm going to factor something out. I'm going to see if I can find at least one x-intercept, at least one point of inflection, sorry. So we have x squared minus 4x. I can pull this out. Then I'm left with -2, x squared minus 4x plus 2, 2x minus 4 times 1, because we pulled that out. Let's set this equal to 0. This gives us x minus, I'm just setting this equal to 0. This gives us x is 0 and x is 4. So those are my 2 points of inflection. But notice, if x were to be 0, or if x were to be 4, would this function exist? Can x be 0 or 4? If x is 0, you would get 1 divided by 0. Not possible. If x is 4, you'll get the same thing. 1 divided by 16 minus 16, 1 divided by 0 cannot be. What that means is that these, although we got them as a solution, they're not part of our domain. Because if x were to be either one of these numbers, we would get a 0 in the denominator. They are not part of the domain. So they are actually not points of inflections. That's the bottom line, is that they are not points of inflections. Although we found them by setting the second derivative equal to 0, they are not points of inflections. So we don't have any points of inflections to work with for this specific question. So the only thing that we could do, I guess, is either you can open this bracket and try and solve this for x, but because we've shown that it doesn't have any points of inflections, I think now we can plug points in. So I'm going to plug f of -1. I'm going to be lazy here. So 1 over x squared minus 4x. Actually, we could have just plugged it in right there. It's a pretty simple function. Let's just do it right here. So f of -1 is 1 over 1 plus 4. You get a positive number. And f of 5 would be 1 over 25 minus 20. You also get a positive number. What this tells me is at -1 and at 5, I'm up here. Now, the only thing that would make sense, remember we didn't have any x-intercept, is the graph looks like this. Cool?
Mhm.
And that's it. That's it for this question. Don't worry, we'll be done with this topic after this. Let's do a fun problem. It says find the horizontal asymptote. To find the horizontal asymptote, you want to find the limit. Like for example here, let's say you have x over x squared plus 1. This is your function. What we do is we say limit as x approaches infinity of x over x squared plus 1. And then we would divide everything. This is for the horizontal asymptote. This is where the shortcut comes from. We divide everything by the highest power. So the highest power here is x squared. So you would need to divide every term by x squared. Here you get 1 over x. Here you get a 1. And here you get 1 over x squared. Now think about it. You're plugging a very large number here, because x is infinity. 1 over infinity, 0. 1 divided by a very large number is a 0. 1 divided by a very large number squared is also a 0. So you have 0 over 1 plus 0, 0. That's where the degree in the numerator, degree in the denominator math comes from. Essentially what we're doing is we're finding the limit at infinity. So this is the same process here. What's the biggest power here?
2.
So it's a little bit complicated, this one. That's why it's here, I think. It's because there is a 2, but it's inside a square root, right? So what's the effective biggest power in here? It's 1. So look at this. This one's going to be a little bit more complicated. So limit as x approaches infinity. X over x, that's the biggest power. But because we have a root in here, because x is just the root of x squared, I'm going to divide both of these terms by x squared inside the root. Plus 1 over x squared inside the root. I'm allowed to do this because inside the root, x squared means the effective power is a 1. So then you have limit as x approaches infinity of 1 over 1 plus 1 over x squared. Now think about it. You're plugging a very large number in here as x. What's 1 over x squared? What does it approach?
0.
0. So effectively you have 1 over square root of 1 plus 0. 1 over 1, it's 1. Let's see, let's verify this. So the horizontal asymptote for this function should be at 1, if our math is right. X over x squared plus 1. Let's see what this gives us. I didn't check for the negative side, but if you could look here, right? If you look here, what is the y value that it's approaching? 1, right? You see that?
Mm-hmm.
It's gonna be 1 the whole way throughout. Now we didn't check this for negative infinity, but if you plug a negative infinity here, what would change? X over x, 1 over x squared, 1 over x squared. So if you plug a negative infinity there on the other side, so that'll be checking the end behavior at the other side. What is it approaching? Negative 1. Negative 1. So ideally you want to check it on both sides, okay? This is a fun little function here. All right, we can call it there for today.
Okay, thank you.
See ya.